It's fantastic to see so many people here tonight and to see that you behave just like students. The front row just isn't filled, so let me give you what I see as the general public's impression of what a statistician is. So I think a lot of people, when they hear about someone being a statistician, thinks that there's someone goes and collects sort of train numbers. Maybe they collect data through sports. They're usually nearly always bearded whenever you see them as well. And then, we get the worst quote ever about our discipline, which goes back to Disraeli, that lies, damn lies, and statistics. Okay, so that's sort of maybe old views. Maybe you hope over time it's got better, but sadly I do dress like a statistician during the day, and I do like statistics most of the time. And this bottom quote, does anyone know the origin of this one? It's almost as eminent as the first one. It's actually Harold Bishop out of Neighbours. He came up with that one. So soap stars really don't like us either. So yes. Okay. So when people do statistics at school, most of the early emphasis is about summarising typical values of the data, and that might be finding means or medians and modes, plotting histograms like this. Looking at maybe at A-level, they look at something called the normal distribution, which has this sort of nice shape. But this is a picture taken off the web. And actually what it does is it chucks away everything that I'm interested in, because what I'm actually interested in is the unusual bits of the data, the ones right out into the tails, sort of the very rarely occurring observations. Now, they're really important to us in many fields. Typical values of weather aren't that interesting, but the extremes are. When you're in a ship, you don't mind typical weather, you worry about the extreme weather. With a stock market, you don't care about typical days in the stock market, whether things go up and down slightly. It's when there's the big crashes that matter. And my typical running times aren't very interesting to you, but the extreme ones are. So what I'm going to try to do is take you through these four areas and give you a little bit of a feel for how type of extreme value, type of mathematics comes through to try to describe and characterise the type of extremal behaviour of things that we see every day. Okay, so take us back to last December. These slides, which don't come out brilliantly, but are courtesy of the Environment Agency, show the rivers last year, the gauges that we have on the rivers over the north of England, which actually got their worst ever river flow during last December. So, the red ones here all got their worst ever flow, and the blue ones, were bad, but not at their worst levels. So you can see last December was pretty much a record level in terms of the flows that occurred. It was the wettest month on record, and it had the worst ever daily total rainfall at a place, which at Honister Pass, so over a foot of rain fell in one day at Honister. If you just break that down in terms of the damage that those set of storms caused in December, we had Storm Desmond, which affected this region up in the northwest, but more centrally in the north, right through from Manchester to Leeds, both Ever and Frank had very substantial effects, and the circle sizes is related to the extent of the properties affected or through flooding, with 17,000 properties in total affected over the three events. So you can see from this that when we get flooding, it occurs not just at a particular place, but quite widespread in its effects. So focusing on the event that we had here last December, here's a very nice aerial picture I hadn't seen before, showing the effects on the industrial units down Caton Road. It was a particularly extreme event. For Lancaster, its major impacts were not because necessarily of flooding, which was obviously bad, but not as bad at many other places, but because of a substation that got affected. That was designed to withstand flooding, they said, once every 100 years. We'll try to explain what that terminology means and how to interpret that later on. Now, this is a very grainy picture, but when you want to actually look at how rare events are, we actually need some data. And many old bridges have markings on them showing flood levels. So if you go to the Crook of Loon and then walk along to the Pipeline Bridge, which is about half a mile on from there upriver, you come to this Pipeline Bridge here, and you can see typically the water level's about 2 metres below the bank level here. But if we just focus on this buttress at the end here, here's the top zoom-in version of this on the side, and there are some flood marks on this from historical floods. And in particular, just zooming in on these bits here, you can see floods in about 1890, 1920, and then 1995 here as being top of a record level prior to this year or last year. So flood levels there aren't, the actual water levels aren't actually that helpful in some sense because the valley is so wide, and at different places looking at the water level itself isn't so informative. So it's much more helpful to look at the flow speed of the river. So these take the worst flow speeds in each of the years at Caton, at the weir at Caton, so this is just near Crook of Loon, and look at how they vary. And there you can see 1995 was, over the period they've been recording this explicitly from 1968 onwards, you can see that it was the worst level. Now, I'll come back to this in a second, but this shows, on this plot, I show extra to this, the 10-year, 100-year and 1,000-year level that would correspond to these data. And I'll explain how I've got these as part of the talk later on. But for the moment, let's just take those as given, that they are a level which occurs once every 10 years, once every 100 years, and once every 1,000 years. So what's that mean? It means that if we're in a type of steady state situation without climate change or anything happening, that the 10-year level would be exceeded once on average every 10 years, or in a particular year with probability of 1 over 10. And the 100-year level would occur with probability 1 over 100. So it's just saying in a particular year we've got a chance of that level occurring. It doesn't mean once we've had an event that's a 10-year level, it won't occur again for another 10 years. It's just saying the probability of occurring in any particular year is 1 in 10. And you can see over basically 50 years of data I've got here, I've got 1, 2, 3, 4, 5 exceedances of a 10-year level. So it's happening about once every 10 years on average. But the 1995 events classified by this as a 1 in 100-year level. So that was until we got last year's floods. And this was obviously one of the pictures from last year's flood taken, I think, from along Caton Path. And if that was record levels, and if we go back to this bridge, if we just look up here, you can see the flood mark on this, and that's basically right up here on the bridge. So you can see it's substantially higher, given that, as I say, the valley there is about at least a third of a mile wide. So it's a substantial amount of extra water that came down in that last year's flood. Now, if we put that point on the data check in terms of the flow rates, you can see it then substantially exceeds the 1,000-year level. So it's much more extreme than anything we'd seen previously. Just give a sense of how extreme it was. It's got this flow rate, which means nothing to any of us, I'm sure, but it was the worst ever or strongest ever flow recorded in any river anywhere in Britain. Okay? This is also useful for the politicians here, but it's 35 times the speed of the Thames on a typical summer's day. So that helps get it over to politicians how extreme this event really was. So what I'm going to try to do is focus on the times at which these events occur. So for this level, which is above the 1,000-year level, it corresponded to a 10-year event, a 100-year event, and a 1,000-year event, and so on. So we can actually, if we just think in each year, we've got a probability of 1 in 10 of a 10-year level, 1 in 100 of a 100-year level. We can look into the future if things stayed very similar to now. We can use computer simulation to do that. And here's a potential future scenario of the times at which we get these events. So in terms of a 10-year level, going into the future, we might have periods where we're really lucky, where we don't get a 1 in 10-year event for 30 years. Or we might hit really unlucky, where we get lots of them occurring in a certain time. This can just happen simply by chance. We can also get, for the 100-year level, long periods without them, but then other periods where we get quite a few in close succession, just simply by chance. But now to look at really what the different chances of those things are, we can work out the probabilities of different scenarios here. So we can, in particular, I think probably it's helpful just to look at the table. What's the probability that we get a 1 in 100-year event, at least one of those in a certain period of time? So in a 10-year period, which is probably 1 in 10, is I'm going to get a 100-year level. But say in 20 years, it's about 18% chance. So I'm reasonably likely to get, particularly if I look at it over 100 years, I'm very likely, more likely than if I could just sing a coin that I'm just going to get ahead, that I'll get a 1 in 100-year event. So it's not that unlikely that I'm going to get a 1 1 in a 100-year event in a 20-year period. But we saw at Lancaster, or at Caton, we saw there were 2 1 in a 100-year events, if we just go back to here, in a 20-year period. So what's the chance of that? So the chance of getting 2 1 in a 100-year events in such a short period of time, in 20 years, is sort of like 1 in 100. So we've been really unlucky in some sense. If these return levels were correct, we've been really unlucky in getting 2 very extreme events in this last 20 years. But there are other possibilities as well. We'll come on to those. So let me just explain how the 100-year events are worked out, because they just seem to be these magic numbers and levels that we've got here. So suppose I was trying to work out what the return level was, or how often, what's the probability of exceeding that red level here, and I've got some data over, say, a 20-year period. So if we just looked at the histogram of the data, we can see most of the values are quite far away from the red one. In particular, no values are above the red one. So it's very difficult to work out what's the probability I'm going to be above the red level if I've never seen any data above there. And that's where we start to have to think about extreme value type of methods that I'll talk about. Now, one possibility we could do, if we didn't really care about things too much, is we could just wait for a long, long time. Let's wait for 500 years before we design any of our flood defences. Then we get much more data, in theory, and we might see over that 500 years we've seen 7 values above, which would then mean that level was about a 1 in every 71-year event. So it's close to a 100-year event. But of course we can't do that. We can't wait to collect more data. So we've got to try to use, from the data we've got, to try to work out what's the chance I get a value bigger than the red line here. So how could we do that? We could guess. But if you think about what the UK spends on flood defences, that's not a very efficient use of information. So, £1 billion is spent in the last 10 years on flood defences. So, just guessing what level we should do to try to get the right required level of protection isn't ideal. Even if we just stop it on a seawall, if we put it a metre higher, it costs us £150,000 more just for a 100-metre stretch. So if we estimate these levels wrongly, we can be wasting an awful lot of money if we put them too high. But if we put them too low, there's obviously going to be serious implications that we'll get flooding much more regularly than we intended. And of course, that would be a way we'd get 1 in a 10 or 1 in a 100-year floods occurring more regularly, simply because we'd estimated the level incorrectly and too low. So how can extreme value submethods, or how can statistics first of all help? So one of the things to do with statistics is we look at the distribution of the data and we try to describe the nature of that variability. And we do it through mathematical curves in this case. And so we try to fit some version of a curve, which obviously isn't quite done here, to the histogram, to describe what's happening within the range of the data that might tell us what goes on beyond the range of the data. And I might get some probability of being above the red line being that. But I could take another distribution I might think looks suitable and apply it, and you can see in this case I get a probability estimate that's sort of 100 times different. So the return period estimate would be 100 times out from one to the other here. Yet actually within the range of the data I've got here, they don't look that different in terms of how well they fit the data. So it turns out those type of methods that standardly come up in statistics aren't ideal in these situations. We really need to focus our efforts much more on what's going on just with the big values. So one way of thinking about this is just to focus on the very biggest values that we get in a particular year. So take my 20 years of data that I had before, partition it into years, and in each year, just pick out the very biggest value, the red crosses here. So now I've only reduced my data set down to just having 20 values. And if I look at the histogram of those 20 values, I get a messy looking histogram, and from that I might want to apply statistical methods to work out the probability of being above the red line. In other words, fitting some curve and working out the probability from above that. So ignore that 1.6. So the question is, what type of curve should I fit? And that's where the mathematics starts to come in. So suppose we started off with two quite different histograms for what the data might look like. So this could be river flows, say, at Caton, and this could be rainfall, for example, in Lancaster on a gauge. And that's maybe the daily data from each of those. Now, if I take the maximum from each of these and look at a histogram of the maximum of those and just rescale and adjust them so they line up with each other, you can see that actually, even though we started off with what looked like very different distributions, very different curves, they've got very close, even just looking at the maximum of 10 observations. By a maximum of 100 observations, we're very close. And by the time we get to the maximum over a year, they're basically dead on top of each other. So what that says is I can start off with quite different distributions, but the mathematics says I'll end up with the same type of curve I've got to fit, which will be appropriate for describing maxima. So just hold your seats a bit here, because we're going to go rough ride on 2 slides here. So this mathematics says that we get the same type of shape curve, whatever the original curves were, once we look at maxima. And that gives us then a strong mathematical justification to extrapolate beyond our data. Now the question is, what's this distribution? This is the one formula I'm putting up in the talk, okay? So mathematicians can't give talks without a formula. So there's the formula. So that's the formula for the curve. There's 3 characteristics we call parameters: mu, sigma, and psi. And I'll just explain what they do and how they control this, the characteristics of this curve. So if I increase mu, it just moves it to the left or right. So it moves it to the right. If I increase sigma, it spreads it out. And if I increase the psi, it just changes how slowly it decays in the upper tail. So what we do is we try to estimate, using data, what these 3 characteristics are, these parameters, and then we can from that do a mathematically rigorous way to extrapolate, to look at rarer events than we've seen before. So that's how, using the data up to last year's flood, I estimated the level at which it occurs once every 10, once every 100, and once every 1,000, according to that. And we saw those were estimates, but they're not perfect, because we've only got a certain amount of data to learn about these from, so we've got to put some uncertainty on those estimates. And actually, you'll be surprised that these estimates are very uncertain. Just using this data, effectively, this 1 in 100-year level could have been as low as this, or as high as this. So there's an awful lot of uncertainty in these, which shows you that, again, when people talk about a 1 in 100-year level, they've estimated it from data, but they could be quite far out. So by accident, then flooding could occur much more frequently than expected, or much less frequently because they've over-designed. So one of the key roles that a statistician has is trying to effectively reduce that uncertainty by learning about these aspects as efficiently as possible to narrow down the uncertainty range. Just to show you the importance of the effect of this uncertainty, just suppose I worked out those different levels again after we saw last year's event. See what happens. So that 1 in 100-year level goes from here right up to here. So it's now, if I estimate it after this, it would be like I'd estimated the 1 in 1,000-year level before. So you can see they are greatly uncertain and particularly very disturbed by very big events that we might try to estimate these using. Now, those of you that might have looked more carefully at the data when we've talked about it before might have actually noticed that it isn't quite stable over time, but gradually there seems to be a bit of a drift. We tend to get the bigger values later. You can see that in the second half of the data is the only time I get values above the 1 in 10-year level. So actually, maybe a more appropriate analysis for these data is to recognise that actually there's some form of trend going on in the data, and actually they're getting worse over time. Now, there's infinite number of reasons there. It could be climate change, it could just be to do with the way the river's been maintained and things like that. But we can use these extreme value methods and tease out and understand about the trends in these extremes, which can be very different than the trends in the overall data. Now, just to push that logic through, if we had a scenario like that and it continued into the future, we can do simulations again, and we see that our 1 in 10-year level just gradually gets more and more regularly occurring until it actually happens every year into the future. So that's a scenario over which events are just getting worse. So what was once a 1 in 10-year level now is happening every year. Now, even though things are getting worse, you can see here that we still might rarely, just by chance, get a 1 in 100-year level. But again, over time, if we pushed it a long way into the future, we're going to get it occurring very frequently. Now, I'm not saying that that trend necessarily is going to continue into the future in that way, but hopefully it gives you an idea that sometimes when people are talking about these levels, if there are sort of small trends in the data, then these levels are going to naturally change their frequency in which they occur. Now, you'd be reassured that the Environment Agency don't exactly work out their 1 in 100 and 1 in 10 year levels using just the annual maxima. What effectively we do in these analyses is, rather than just using the maxima, we use all the values which are extreme as judged by being above some high level. So we use all the sort of major flood events. We take information from different gauges which have similar characteristics and pull that information to learn as much about the data as possible. And so that will typically narrow down that uncertainty range very substantially. So that's all to do with rivers. Now, one of the things I actually did my PhD in and worked in for many years before I started working with river data was to look at sea level extremes. Now, sea levels are slightly different than river levels, and the key difference is the tide. I think you all know that if you go to the coast, if you go there 6 hours later, the sea level will be quite substantially different. If you go at high tide, 6 hours later, it's going to be low tide. 6 hours later, it's going to be basic back to high tide. And so when you look at the extremal characteristics of the sea levels, you've got to take much more careful account of the tide and the non-tidal bit, which is called the surge. So the surge is due to the weather systems moving over, whereas the tide is predictable simply by the movements of the planets. So what we've developed is ways of looking at the extreme surge and combining them back with the tides to get understandings about what these 1 in 100, 1 in 1,000 year levels would be for sea levels around the UK. And in particular, we can pull information along a coastline to tell us about the extreme surge, because that changes really nice and smoothly. Whereas you know, just from your own experiences, if you go from one place to another, the tides change quite rapidly, and we can use numerical models to see how the tidal characteristics change around the coast. And so we've developed the methods that are used whenever you see any coastal flood defences being built. We've developed the mathematics and the estimates from those that are actually used to decide how high to build the seawalls, how big that 1 in 100 year level should be at any new design around the coast. Now, what I've talked so far about is just flooding at a single point. But you saw back at the original slide that flooding doesn't just happen at a single point, it happens at a set of gauges all in the same event. So if we're just worrying about stopping flooding at a single point, we'd be thinking about these return levels and estimating those. But in terms of the impact of it over a space, then there's a range of things. The government's very interested in how often big flooding events happen at different places over the country, how many different sites are affected at the same time, because that affects how their resources are spread in terms of how much resource they need to put in overcoming the impacts of a flood. If it's very narrow, very localised or very widespread, it has a very substantial difference to government emergency planning. And from insurance perspectives as well, that makes a huge difference. If all the floods occur and only affect very local areas, the costs that they pick up are going to be quite small each time there's an event. Whereas if it's a very widespread event, the flooding is going to occur over much larger areas of the country, and they'll get suddenly a whole set of claims in over a big set of numbers of customers they have, and suddenly they get this huge lump sum of claims, and they have to handle that. So what you've got to think about when we start to look away from just looking at one site, you've got to think about questions like, what's the chance that we'll get a 1 in 100 year event occurring at maybe different sites at the same time? And that's where we've developed particular theories, both mathematical and statistical methods, which allow us to look at this. And just like in that case where I showed you those two curves got closer and closer as we looked at maximum of more events, the same type of mathematical ideas come through in that case. And so we can narrow down, out of all possibilities, we can narrow down and look at a subset of cases. So here's some recent work we've done, which is fed into the National Flood Resilience Review that came out at the end of September. So this is work I did with a hydraulics research company at Skipton JBA, and we have a long relationship with working with them. So here we were asked by this resilience review to look at the chance of multiple flooding events at different sites. So Scotland, strangely, Britain's not very connected in lots of things. Scotland likes to be treated differently in all respects. So we will just look at England and Wales, and these are the gauges in England and Wales which had at least 20 years of data. So we were interested in what's the chance that at least one of these gauges has a 1 in 100 year event. So we ask, what's the probability at least one gauge in the country in a year has a 1 in 100 year event? Now, if they all got a 1 in 100 year event at the same time, this would be the probability. So as we looked at different, what's a 1 in 100 year event, it would be, the probability of it would be 1 in 100 if everything got flooded exactly at the same time to the same level. Whereas if they sort of flooded completely unrelated to one another, it would be right up here, it would be 1. Of course, you see, to the government, that's a very big difference between 1 in 100 and 1. And they needed to then characterise to see where do we sit somewhere in between here. And what we're able to use with our statistical methods is effectively to find where the curve really fits in between those, to say, well, actually, a 1 in 100 year event happens somewhere in England and Wales with probability 0.8. So there's a high chance in a particular year, somewhere in Britain, we'll get a 1 in 100 year event. Can't say from that where it's going to be, but somewhere in Britain we'll get a 1 in 100 year event with a very high probability. We can look at different units of resource where they've got to, where they manage flooding events. So we can look at what's the chance that of these different type of resource areas, what's the probability that one of them's affected, or two's affected, or three's affected, if the events are 1 in 100 year type events. So we can look at all sorts of type of risk analyses once we can describe this dependence between the flows at the different places. And in particular, going back to this situation we talked about at the beginning, what's the chance that we're going to get 2 of these nasty 1 in 100 year events in a 20-year period? We saw at Caton it was sort of 1 in 100, but over the country, somewhere's going to get it. It's 95% certain that somewhere's going to get 1 in 100 year events in 20 years. It's just we've been the unlucky people in the Northwest in this last 20 years to get this. So that's the work for Resilience Review, and then more recently than that, we've been longer term project than that, we've been looking with the insurance companies, and here's just an illustration of the types of work we've been doing with them. So here's a zoomed in map showing all the rivers in the northeast of England. So there's Newcastle, Middlesbrough, I guess that's Sheffield. Is that Leeds? Thank you. Yeah, Hull. So you've got some scale on there, and the red dots are the gauges where we've got data for river flows. Now, everywhere along this river network, every type of like 200 metres, there's an estimate of what type of loss will incur for different return level events. So if the water level was this high, what on average would we expect for damage to be? And we've got that everywhere along that whole river network at every 200 metres. So in particular, if you look at something like this, here we've got the University of Hull, which is this brown one. So it's protected up to a 20-year event, would be no loss, but after a 20-year event, as we go to more rare events, its losses go up very substantially as the water level rises. And we've got that at every different place along this network. Okay, so it had to happen, didn't it? So if we look at the past data to look at the biggest losses that have occurred in terms of financial loss now, rather than over that whole region, it occurred in this event here. So these are showing the river flows. You can see it's actually a 1 in 500 year level near Newcastle, and we can map that loss down the network here, and then along there we estimate the total aggregate loss to the insurance company if they're insuring everything in that region. But if they're only insuring subsets of that, then they'd scale down these curves appropriately. So we can look at the worst case, but we can also look at future scenarios using the fact that we know how to model the joint characteristics over different gauges. So these next set of maps are all 1 in 100 year loss events. So they all incur the same financial loss to the insurance company, even though at different places they'll have different levels of extreme. So this is an event where you can see it's actually at its most extreme, probably near York. So that created a bad loss there. This one's extreme near Middlesbrough, and then this one's in Northumbria. So you can see that in these 1 in 100 year events, we've got little bits where they're 1 in 500, little bits where they're 1 in 10 years. But overall, in terms of the loss that occurs, it comes out as a one in terms of as a 1 in 100-year event because of the values of the properties. And again, we can look at that situation where if every site was unrelated to each other, that would be how the losses would combine. If every site got flooded at exactly the same extent together, that would be the losses, and we're able with our methodology to fill in the missing curve in between to understand how the dependence really works. Okay, so let's move on to my shipping example here. So I don't know if you've heard about the MV Derbyshire, but it actually still remains the UK's biggest ship that's lost at sea. In 1980, it sunk in Typhoon Orchid on its way to Canada, and all 44 people on board died. Strangely, there was no Mayday, and for years people wondered what had happened, but eventually they managed to do underwater photography of the wreckage and then started to investigate what was going on. And the early stages after that, they thought it was to do with the way the crew had maintained the ship. But loads of different scenarios came up. This report from this video was developed before I got involved in the court case.
As the typhoon approaches and conditions worsen, the master, following normal practice, turns to keep the waves at a slight angle to the bow.
So this ship's 2 football pitches length in length and about a 6-lane motorway wide.
The vessel begins to take heavy waves of increasing frequency and intensity over the bows. The foredeck stores hatch cover is carried away, so that the bosun's store space fills with every wave over the bow, probably filling in less than an hour. As the main force of the typhoon approaches, the seas worsen even more, with substantial green seas crashing onto the foredeck. Damage occurs to deck fittings. The ventilator tops are carried away, leaving the ventilators open to the sea. The four-peak ballast tank takes on water with every wave, and in some 12 hours is more or less filled. The vessel becomes more sluggish, and 25-metre waves sweep over the bow, putting pressure on the first 3 to 4 hatches. A large wave crashes over the starboard side of the bow, destroying the hatch covers on number 1 hold, allowing thousands of tons of water into the hold. All forward freeboard and reserve buoyancy is lost. Number 2 hold hatch covers collapse under the weight of water.
So this first hold that's gone is
the next hatch
key.
Cover is driven inwards by wave pressures as number 1 tanks implode.
So this is where you realise it's a very long ship, and basically we're able to show that
this process rapidly dominoes along the length of the vessel, becoming increasingly violent as the ship slips below the seas and the angle increases.
Yeah, so once the first hold goes, basically it's automatic the ship's going to sink.
Shock waves traverse the structures, weakening them and making them more susceptible to collapse towards the aft end of the ship.
At this point you always think, just sink. Get to see what's going to happen.
Implosions at the forward end of the slop tanks rupture the engine room structures. The pump room and part of number 9 hold, and the weight of the engine, tear out the double bottom. The stern immediately fills, sinking below the surface. The accommodation, already seriously damaged, separates below the surface.
This isn't a key bit now.
The time elapsed between the collapse of number 1 hold hatches and the sinking of the stern is about 2 minutes.
Okay, so there'd been this investigation. They'd have understood basically the process by which things happened that hold 1 broke. They wanted to understand better about quite how it got to that stage. So you saw those early front end of the ship gradually filling with water. They wanted to understand what, did those actually happen? What was the effect of different elements of those front end filling with water? And also understand how, if the ship was run differently, if it was run faster or slower into the waves, would that have had an effect? So the design cover for the design strength for the front hatch cover was 42 kilopascals for the wave impacts on that. So the courts were interested in what was the probability of getting a wave impact that exceeded that design level depending on these other characteristics. Now you think, well, how on earth can you do this? The ship sunk. But you can find out about what the wave climate was during the typhoon, and that obviously changes through the time of the typhoon. You can build a little model of a ship and do wave tank studies looking for different type of variabilities of the waves, looking at the impacts on the hatch cover. And what our contribution was we looked at then the distribution of those wave impacts on the hatch cover. So before I was involved in the court case, these numbers are slightly updated because these are mine after getting involved. They were looking at a range of different scenarios. So the ship was intact, it didn't get any of that front-end damage, but the waves were as predicted or maybe a bit higher, or that some of those different areas at the front were broken, filled with water. And you could see that pretty much the probability of a ship sinking under their first idea of what the distribution might be for how the wave impacts were was pretty high, whichever of those were. So that made it difficult for the courts to decide which of these routes it was, because in some sense all of them were very high probability. But during the investigation that was happening at the High Court, it was proposed to consider a different statistical distribution. And you can see here now that pretty much whichever of these scenarios, it was somewhat unlikely for a ship to have sunk. So their ability to decide which was the cause between these different features was really lost and swamped by the statistical uncertainty on the distribution. Very much like when I showed you that plot at the beginning, the probabilities were out by a factor of 100. Actually, what they needed to have done was model the extreme wave impacts on the ship using the extreme value methods we work with. And when they did that, we can get probabilities there which we could give uncertainties to the court and give a much clearer idea of what was the potential route here. So in other words, what this is saying is it was very unlikely the ship would have sunk if those front-end areas hadn't filled with water, even if the waves are quite a lot higher than predicted. But maybe you needed that big ballast tank to fill with water to have a chance that the ship's going to sink. It'll get an impact on that front hatch so big. So the judge in his summing up said that our work was actually the fundamental element to deciding the cause of the sinking of the ship, which is scary how a statistician can do this to 20 years after the ship sinks, and asked us to do the work to develop new design strengths for hatches of all type of similar ships to this. So now we've got new worldwide standards that are developed using the mathematics and results that we got from that, which have led typically to the front hatch cover being 35% stronger than it was before as a design standard. And basically, many of the ships have been, 2,000 ships have now been designed to that new standards, and it's actually that coupled with a lot of other changes that happened around the same time have massively reduced the number of losses since then. Have I got time just for one last topic area, just to give people a feel? Okay, so one other area of extreme values is, and in the statistics, is in banking. You always hear about these people, these quants, and they do all these fancy bits of mathematics. But actually, because of their behaviour, they basically killed Wall Street in the crash of 2007. And it was all because of this mathematical formula. Okay? What it's type of saying is it's like saying what's the probability of a stock market, one stock being small at the same time as another stock being small. So it's describing the relationship between stocks. Do they get small together? And they'd been started adopting this formula to help them assess the risk in about 2000. It's called the Gaussian copula, but details aren't important. But they basically misused it because it wasn't appropriate for the data they were looking at. So could we have done better? Well, yes. In fact, they should have used extreme value methods because they were looking at rare losses with other losses. And so we know that the Gaussian copula has this property that it doesn't allow big losses of one stock and the other one at the same time. Yet the data clearly showed that was possible if you just looked at the data. So they massively underestimated the risks and therefore got into this situation where they made losses that then perpetuated through the system. What did they need to do? They needed to use this same mathematical theory that we were using to look at floods at different places. It's just the same as stocks at different forms of stock, looking at chance that they get big at the same time together. And so the mathematics that we do for spatial flooding actually helps answer exactly the same type of question to do with the stock markets. And these methods are now starting to be used much more actively in finance. And if I really have one last minute, it's just as a fun one to finish with. Who's the best ever track athlete? How would you go about thinking about who's the best ever track athlete over athletes? So here's some potential candidates. We've got Bolt, we've got Flojo, Michael Johnson and Co, who I've stretched a bit. I don't think he was quite that fat in his prime. So how can we do it? Well, actually, we use the same type of methods as we looked at flooding, recognising that, of course, in athletics, the times that they run now are nothing, orders of magnitude faster than in the past. So you can't judge best just by what people do as the very fastest they've run, but it's got to be relative to their peers at that stage. And so here you could see these ones with the flooding, they weren't the 1 in 10 year level, but once we accounted for the drift in trend, they became apparently more extreme. We can do the same thing just to rank which is the most extreme when we account for the different trends over the different distances. And rather strangely, you see from this, Flojo does turn out to be the best female athlete. We had a new one enter the top 10 in the last Olympics, which was the 10,000 metre gold winning one. No new ones coming in the top 10 for the men's. You could, if you very sceptical view, this is a list of the biggest drug takers, but I wouldn't say that in public. But there's some strange names there you wouldn't necessarily expect to see, but also a lot of names you would. So, very final slide. Hopefully, I've given you a sense of what statisticians do. I hope we're not at that end of a spectrum and we're close to that end of a spectrum. But thank you very much for your attention today.